Welcome to the first part of a Raytracer series. I'm gonna create the start of a Raytracer today, and we start with a clean desktop project with Jetpack Compose. First, we clean up the files from the template and remove the things that we don't need. And now we can start adding code. We start by creating an image canvas, which will be the area where we will render our finished image after ray tracing. It's based on the canvas, and as always we give it a modifier. We draw our image, and the image we also add as a parameter. And the last thing we need here is to make it listen to the size changes so that we can react on resizes. We get our image from the model, which I have not created yet. So we do that, and we will call the model the view model. We also make sure that we tell the model whenever the canvas changes size. We create our view model. And add the image, and we add the onSize changed callback. The image will be of the type state flow, so we can listen to it. We initialize our image with a render method. And the initial size will be 1 pixel by 1 pixel. And whenever the size changes, we update the size. To save some memory, I will create an image buffer that will contain the image without recreating the memory footprint every time. So let's create that class. It will be of the size that the canvas have. And we create an array where we will save the data for our image. It will be of 4 bytes, 1 byte for each color channel and the alpha channel. We create the render method, which will take a function that will be able to render 1 pixel at an XY value that will be between 0 and 1. And for that we need to create an RGB class that just holds the red, green and blue value for that pixel. And I will create a function that will go through the byte array. We loop through the height and the width of the image so that we can render each pixel. We take the pixel value and convert it to a value between 0 and 1, so we can send it to our function and ask it for a pixel value of that position. When we have the value, we put it into our array at the offset that we can calculate from the x and y value. We convert the bytes into an image. We're using Skia, which is part of Compose, and we and the Skia image we then convert into a Compose image and return it. In our model's render method, now we can make use of the image buffer and render and to test it, we just render a gradient so that we take each x value and each y value and convert it to a color. And now when we run it, we will see a gradient. So now we can start doing some 3D things, and with all 3D things we need a way to define points in 3D space, and we use a vector 3D class that defines an x, y and z position in 3D space, and we define some mathematical operations on it. Start with plus, it's simply just adding the x, y and z components respectively. And we do the same for minus subtraction, and also for the unary minus, just to invert a vector. And multiplication we define by multiplying with a constant that is that can be seen as scaling a vector. A value larger than 1 will make it larger, and a value below 1 will make it smaller, and a negative value will invert it. Division is the same thing, but just the opposite. Some other common operations are the dot product, which will calculate the angle between two vectors, or more specifically cosinus of the angle between two vectors. The cross product takes two vectors and returns a third vector that will be orthogonal to the two given vectors. So if we give it x and y vectors, it will return the z vectors. We also create a function to reflect a vector given a normal, so it will give back the vector that is bouncing off a point with a given normal. For this calculation we need the normalized version of a vector, that is a vector pointing in the same direction, but with a length of 1. And to make it length 1, we divide it by its length, and the length is calculated by Pythagoras. So we square root the squared length. We also create a property for the inverted vector, that is this vector that is just pointing in the opposite direction. And to be able to multiply a vector with a constant on the left side of the multiplication sign, we create an extension method. And we also create some convenience object, that is the normalized x, y and z vectors. And finally I will create an extra constructor. It's only for convenience, so we can put in any values as parameter to the constructor, but we will convert them to floats. And we fix up some mistakes. And now we need something to actually render, and we will create a sphere. A sphere is the easiest thing to render in a Raytracer. And to make it even easier, we create a sphere that's always positioned at origo with a radius of 1. We need a function where we can calculate an intersection between a ray and a sphere. So we will also create a ray class, which is a class that contains the origin of the ray, where it starts, and the direction of the ray. And the ray will also be able to calculate the point at which a specific distance is from the origin of the ray. The intersection will also be modeled, this time as an interface, because we need to be able to represent a miss and a hit. The miss will just be an object, but the hit must be able to provide a hit point and a normal at the hit point. We will call our hit the surface hit, and it will remember which ray was used to create this hit and the distance on the ray where the hit point is. And we will also give it a function that will be able to calculate the normal for this hit. Calculating the intersection will be done using a simplified version of the sphere ray intersection. A is the ray's direction, dot product with itself. B is the origin of the ray when the dot product with the direction. And C is the origin with dot product with itself. And we subtract the squared radius, which is always 1. The discriminant, that is what we're going to divide with. to be a hit, it have to be larger than 0. And since a sphere can hit a ray at 2 places, we first check T0, which is where the ray enters the sphere. And then T1, where the ray leaves the sphere. And then we return the respective hit point. And that's all we have to do for calculating the hit point of a sphere. And now we need something that shoots the rays, and we will call it a camera. I will create a simple parallel camera, that is a camera that shoots all rays in parallel, so it won't give us any perspective. We create the viewport of the camera by giving it the center point, one vector that is half of the width and one vector that is half of the height, left and up. And we calculate some constants for the camera. The direction is the direction of all rays, top left corner, the width of the view, and the height of the view. We create a function which will be able to retrieve a ray at a xy value of the view. X and y is between 0 and 1 in this case. In our view model, we create our camera. We put the origin point on the Z axis, and we create the view in the X and Y axes. We create a sphere, so we have something to render. And inside our render method, for each X and Y, we ask the camera for a ray. And check if that ray intersects with the sphere. If it doesn't intersect, we keep our gradient as a background. And if it intersects, we paint that pixel red, so we will get a red circle. The circle do fill our whole viewport, so I will make the viewport a bit bigger, so it will get a red circle at the center of the image. Resizing the image do make this sphere look skewed, so we have to fix that by making the camera consider the aspect ratio of our image. We create a function that creates our camera and takes the aspect ratio as a parameter. As default, we use 1 as aspect ratio, and then every time the image is resized, we create a new camera with the correct aspect ratio. There, it looks much better. Now for some shading. We create a light, that is a position where we imagine a light somewhere above our right shoulder. And in our intersection calculations, we check the direction to the light from the hit point. We find the normal from the hit, and then we calculate the angle between the normal and the direction to the light. If this angle is larger than 0, we use that angle to shade our pixel. There it starts to look a lot more 3D. We can also take the angle between a ray reflected at the hit point and the normal. And use that as a highlight of our shading. We add that to our total light. We do see some artifacts. That's because we need to force the value to be between 0 and 1. And there it looks better. I will make the highlight a bit smaller. And there we have our ray traced sphere. I will end this episode here. Thank you for watching.